Why do we even need a database? To store data, but can't we just store everything in the application server's memory? Well, in the last scaling video, we saw the problem. Once you scale out to multiple servers, data becomes inconsistent across instances, and if the server restarts, everything in memory is gone. So we need databases to persist data reliably, survive failures, and handle scale when a single server is no longer enough. That leads us to two major categories: SQL databases and NoSQL databases. Let's look at SQL databases first. They are designed to store data in a structured and tabular format. We have tables, rows, and columns, and tables can have relationships with each other. For example, an e-commerce application might have a customers table, an orders table, and an order items table. Each table has a primary key and a foreign key to define their relationships. Once relationships are defined, if we want to get order items for a specific customer, we can easily join the tables, filter by customer ID, and get the result we want. So one of the strengths of SQL databases is that the data strictly follows the structure and relationships we define. Another strength is that SQL databases support ACID properties. So what is ACID? Let's break each part down with a simple example. A stands for Atomicity, meaning all or nothing transactions. For example, when a customer places an order, we need to do three things: create the order, reduce inventory, and record the payment. Imagine the order data is already inserted into the table, and the inventory data is also updated, but the payment fails. Depending on functional requirements, we can either keep the order and inventory data and mark the order as pending payment, or roll back everything and redirect the user to a failure page. But can the database actually roll back the changes? Yes, we can handle this by wrapping all three operations inside a transaction. When one step fails, everything will be rolled back. No order data is stored and no inventory is reduced. All or nothing. Next, C stands for consistency, meaning the database always follows the rules we define. For example, if a column is marked as not null, the database will reject any transaction that tries to store a null value. Or if we define a rule that an account balance cannot be negative, any transaction that violates that rule will be rejected. The same applies to foreign keys. If friendships.friendid equals 123, but user123 does not exist, the database can reject it. So we won't end up with rows containing null values in important fields or invalid data like negative prices, because invalid entries are rejected before being inserted. As a result, the database always remains in a valid and consistent state, and that is consistency in ACID. Next is isolation. It means multiple transactions can happen at the same time without affecting each other. Imagine an online store with only one laptop left in stock, and two customers try to buy it at exactly the same time. Without isolation, both transactions might read the inventory as one, and both place an order, causing overselling. In SQL Server, databases solve this using locks and isolation levels. For example, in the read committed level, when transaction A is updating an inventory row, it locks that row. So, if transaction B tries to access it, it has to wait until transaction A commits or rolls back before it can continue. The laptop example is a simple way to explain isolation, but in real systems, isolation alone doesn't always prevent overselling. We often combine it with other techniques like optimistic concurrency tokens, which is a different topic we can explore in a future video. Next is durability, which means once a transaction is successfully committed, the data is permanently saved. Imagine a customer completes a purchase and receives an order confirmation, but 1 second later the database server suddenly loses power and shuts down. When the system comes back online, the order should still exist in the database, and the customer should not lose it just because of a crash or power failure. That is durability in ACID. So when ACID is important for your system, SQL databases are usually the right choice. Then what's the downside for SQL databases? It's hard to do horizontal scaling. Imagine a single transaction updating 4 tables. Keeping that transaction ACID compliant across dozens or even hundreds of servers becomes difficult and expensive. That's why when an SQL server hits its limit, instead of going for horizontal scaling, the first step is usually vertical scaling, buying a bigger and more expensive server. But for systems that generate massive amounts of data at a global scale, you eventually hit a wall where no single server is enough. Also, not all data requires strict ACID guarantees, and some features don't need heavy schemas or relationships, which is where NoSQL comes in. NoSQL means no tables and no strict schemas. It is more flexible and has the ability to scale horizontally, and it is an umbrella term that includes 4 main types. Type 1 is document databases like MongoDB. Instead of rigid tables, data is stored as flexible JSON-like documents. In SQL databases, data is stored in rows and columns, and sometimes you'll see optional fields left as null. But in MongoDB, each record is a document. And if a field doesn't have a value, we just don't include it in the document. That makes the structure more flexible and much easier to evolve over time. Let's look at an example. Imagine an e-commerce system where users choose different product variations. User A chooses a red model A, 10 pieces. User B chooses a black model B, 30 pieces. User C chooses a red model B, 40 pieces. Every user looks slightly different. The structure is not fixed, so instead of forcing everything into many tables, rows, and complex relationships in a strict schema, you can store each user's selection as a single document in MongoDB. It's simple, flexible, and easier to evolve. And this is where MongoDB shines, because it supports a flexible schema and horizontal scaling. It becomes a strong fit for use cases like this, where the data is highly varied and constantly changing. Type 2 is key value stores, like Redis, where instead of tables, data is stored as key value pairs, like a massive dictionary. You give a key and it directly returns a value, making reads extremely fast. Since data is stored in memory instead of disk, like HDD or SSD, both reads and writes are very fast, which makes it ideal for caching. Type 3 is wide column stores like Cassandra, designed for fast writes, low latency reads, and high availability across regions. Imagine Netflix logging exactly where millions of users pause their videos every second, which means huge numbers of writes happening at the same time. Using a SQL database here would be overkill. Every write might need to update indexes and enforce strict constraints. And in this kind of scenario, ACID guarantees usually aren't the top priority. Cassandra takes a different approach. It often writes new data sequentially and merges it later. Sequential writes are much faster, allowing Cassandra to achieve extremely high write throughput while scaling horizontally. Other high write use cases include capturing every user click for analytics and recommendation engines. In these scenarios, high write throughput is critical, and ACID isn't the top priority because missing an occasional click is usually acceptable. That's why Cassandra is often a great fit for this kind of user behavior data. Type 4 is graph databases like Neo4j, which are built specifically for relationships. In SQL, if you want to find friends of friends of friends, you need multiple joins, and each join is expensive, making the query slower and slower. In a graph database, you start at a node and follow connections step by step without joins. The cost depends on how many hops you traverse, not the total size of the database. Since graph databases treat relationships as the most important part of the data, they are extremely fast for use cases like mutual friend recommendations. So now we know that one of the strengths of NoSQL is that it is easy to scale horizontally, meaning the data is distributed. When it comes to distributed systems, there is an important system design idea called the CAP Theorem, which stands for consistency, availability, and partition tolerance. In a distributed system, you can only fully guarantee 2 of these. Consistency means everyone sees the same data at the same time. Availability means the system always responds. Partition tolerance means the system still works even when network nodes cannot communicate. In real-world distributed databases, network failures are unavoidable, so partition tolerance is essentially required, which means systems usually trade off between consistency and availability. Let's see an example. Let's say a video currently has 10 likes. User A clicks the like button, so the like count becomes 11. However, because the data is replicated across multiple database servers around the world, user B might still see 10 likes for a few seconds. At that moment, the system is technically inconsistent because different users are seeing different values. But for a feature like a video's like count, that is usually acceptable. User A can still like the video immediately, user B can still watch the video without interruption, and the system remains highly available. After a short period of time, the update propagates to the other servers, and everyone eventually sees 11 likes. This is called eventual consistency. The trade-off is that we temporarily sacrifice strict consistency in exchange for better scalability and availability. In this case, we are choosing availability over consistency. We would rather allow users to continue liking and watching videos, even if some servers have not received the latest like count yet. For social media applications, this trade-off is often worth it because a few seconds of delay in a like count is usually not a big deal. How updates propagate between servers is something we'll cover in a future video. For now, we'll stick to the core concepts. When we talk about consistency in the CAP theorem, remember there's also consistency in ACID. This is where things can get confusing. ACID consistency and CAP consistency are two different things. ACID consistency means the database stays in a valid state and all constraints are enforced, while CAP consistency means every node sees the same data at the same time. In the context of distributed systems and NoSQL databases, consistency usually refers to CAP consistency, and many NoSQL databases trade strict consistency for scalability and availability. They often use eventual consistency, which we discussed just now. But that raises an important question. Does NoSQL mean there's no consistency at all? The answer is no. Not all NoSQL databases work this way. Cassandra lets you choose between stronger consistency and higher availability depending on your needs. The key idea of NoSQL isn't no consistency. It's flexibility in the trade-offs between consistency, availability, and scalability. And now we come to the final question. Should we choose SQL or NoSQL? The answer is, don't pick either one right away. Instead, start by understanding the problem you're trying to solve. Then, for an e-commerce system, it usually looks like this. For core billing and order management, we use a SQL database because we need strict data integrity and ACID transactions. For product catalog data, we use a document database like MongoDB because product attributes and user selection options can vary widely. For user sessions, we use a key value store like Redis for fast access. And for user clickstream analytics, we use a wide column store like Cassandra. So here's a quick recap. Databases exist because servers are temporary, but business data needs to survive restarts, failures, and scaling. SQL databases store structured data with relationships and strong consistency through ACID transactions, and you use them when data integrity matters. NoSQL databases, on the other hand, provide flexible ways to store and scale data for different types of workloads. And most importantly, choosing between SQL and NoSQL isn't about picking a winner. It's about choosing the right tool for the right problem. In the next video, we'll go one step further into databases and look at replication, read replicas, partitioning, and sharding. So subscribe if you're interested. And if you haven't watched the scaling video yet, I'd recommend checking that out first to understand vertical scaling, horizontal scaling, and auto scaling. See you in the next video.